All right, gang, welcome to the Parameter Estimation Lab. So, in this lab, I want to sort of create this environment that, or this situation that you might be in where you are tasked to estimate the model of the system. All right. So, just like we've been doing in SysD all semester, we've got a system. We want to model it because there's a lot of things we can do with it. Figure out control theory or just analyze, do analysis, etc. Okay, so it's important that we get a model. Now, sometimes you can get the model. You've got sort of the idea of the transfer function, the idealized elements, but the problem is you don't have the values of the coefficients, the MBK, for example. So the question is, how do you get those? Well, there's a few ways, right? We can, for example, from SolidWorks, if you've got a design, you can figure out the mass. If you know the material properties, SolidWorks will give it to you. It'll also give you the inertia. It'll give you, things like that. So that's one technique. Another really important technique is actually fitting, for example, if you have a transfer function, you could fit a response. If you do a step response, do an experimental step response and then fit the model on top of it. So basically this actual lab is still under the umbrella of system identification. But it's not black box, it's gray box. I know the transfer function, but I don't know the parameters. So that's what we're doing today. We're doing gray box parameter estimation given some system. All right. Now, what else is cool is about this lab is this is the only lab where we actually play with a mechanical system. So our model is mechanical, and we actually see the response. Instead, it's not just on the 82. In fact, we're not using the 82 or any oscilloscope function generators for this lab. So that's kind of fun. It's fun, we're in mechanical engineering. It's nice to see a mechanical system, even though all the things that we learn in these labs, even though we primarily have used circuits, it's just a system, and I really want to push you to just forget that it's a circuit. But today it is a mechanical system. All right. So first things first is to introduce you to the system, and then continue on through what you're going to do in this lab. All right. So have fun. All right, for this lab, we're going to be using the ECP torsional system, and I wanted to show you what it is composed of. So you'll notice that from far away, we'll get a little closer, you'll see there's 3 discs with a couple of, the bottom disc has 4 brass masses, and the middle and top have only 2 attached to it. And let's check out each one independently. Now, the bottom disc actually has the motor. So the torque input is on the bottom disc through a pulley system. Okay. Actually, you'll get a better shot over here. There it is. Okay, there's the motor. And there's also an encoder so that we can measure this experiment, to measure the angle or the angular rate of the bottom disc. And of course, there's a bearing to allow it to rotate. Okay. Then this disc is connected by a shaft, hard to see, to the middle disc, which also has an encoder with a little tiny pulley to connect the rotation to the encoder. And here you have the middle disc, there. And then again, same shaft to connect the middle disc to the top disc, all right? And you'll notice these, hard to see, but these brass, the center of the brass masses are right on that second, or on that last ring before the edge, okay? Now, my first question to you is, what order is this system? Let's play with it for a second and think about, what I want you to do is I want you to think about what order this system is and how you would model this as with idealized elements. All right, I actually want you to pause right now and try to answer, come up with a guess and try to answer my question about the order of the system. And then shortly I will actually tell you what the order of the system is. Okay. All right, let's connect this thing to the real world. So this could be a good analogy or model for a satellite. Okay, so imagine that the bottom disk, which has the biggest inertia, is the body is the body of the satellite rotating. Okay, and then the motor itself, which is producing the torque on the body of the satellite, is the thrusters, let's say, that produce that torque. If we're talking about what is known as attitude control, which is pointing the satellite, so here, anywhere I go, let's say I want to point it, 30 degrees. I'm here, I want to go 30 degrees or something like that. So, and then of course, the flexible structure on top of that, which is lighter, but yet connected in a with some flexible spring, could be considered the solar panels, right? So you can imagine that if I take the satellite and I rotate quickly, does it make sense that I'm going to impose that sort of potential energy in the springs, and when I get to the 30 degrees that I'm trying to point at, the springs and the solar panels are going to release, and they're going to then reverberate back into the satellite, and the satellite's not going to be doing a good job at pointing. It's going to be oscillating until it dies out, right? So, and we can see that here. Let's just do it. Okay. So you can see if I try to rotate, I'm having trouble keeping it because of that. So, one thing we're not going to do in this class or in this lab, but one thing to think about is, once I have a model, which is what we're doing today, I can try to figure out what would be the right profile to get it to go 30 degrees without exciting the other flexible modes. Now, obviously, a simple solution you can imagine would be just to move slow, okay? Which is great, but not great. I mean, you get rid of the flexibility and the vibration in the solar panels, but you're also rotating slowly. What if you want to? So what we want to do is try to move as fast as possible, but yet without exciting those modes. So that's an advanced problem. But the way to think about it is can you imagine if I rotate maybe past, or maybe I rotate almost to 30 degrees, but then as the springs tighten up, I then change direction and come back to release that energy before it starts going crazy, and then I move just a little bit more without the spring, maybe slowly. So it's kind of this, you can imagine creating a profile that moves fast but yet releases the spring potential energy before finishing so that it doesn't oscillate. All right? So, yeah, that's sort of the real world connection. Satellite body and then solar panels, and a future problem in a controls class would be, after you model this, then designing the control algorithm where you can move as fast as possible without exciting those modes and being as stable as possible. All right. All right. So now I want to come back to the order of the system. So if you guessed sixth order, then you're right. The way you can get sixth order is by think about the differential equations that you would get. Okay, if you think about it, there's going to be sum of the moments equals I alpha for every, and alpha is theta double dot. So if your output is angle, that's assuming my output is angle, and my torque at the bottom disk is my input, then you're going to have a I theta double dot about each disk, which gives you 3 coupled second order differential equations. And then when you do Laplace and get the transfer function, you're going to end up getting sixth order because of the 3 second order systems. All right. So now, of course, there's a problem with that. To find the parameters of a sixth order system is going to be very difficult. Doable with advanced techniques, but we want to try to see if we can reduce this order, simplify our experiment to try to still get these parameters that we're interested in, but in a much simpler way. All right? We're going to see that next. All right, so let's talk about reducing it. So if I go to the DocCam, first of all, I'm going to draw sort of the idealized element representation of this system. Now I'm going to use a linear analogy because it becomes the same differential equations. So you have B1 for let's call this I1, theta 1, where this is the bottom disk, let's say. Then I have a damper and actually, no. I'm going to assume there's no damper between. There is a spring between. Let's do the spring. This is I2. And another... let's draw it a little bit. Let's shift it up. So this is I3. This is the third disk. This is theta 2, theta 3, and now I've got to draw the bearing. So that one's easy. The first bearing's easy. So the bearing, and then the second bearing, I'm just going to draw it sort of like this. I'm going to draw another ground. Oops. And draw a damper. So think about it this way: if there was a damper between the two, then if they rotated together, if their angles were together, then you would you would get no energy loss, which is not true. Just by rotating the bearing, you're going to get energy loss by both. So that's why I'm going to put the second damper to ground, and same with, and let's call that K, and this is K. And then I'm going to do my third damper also to ground. Actually, I'm going to do it on this side. And there's B. So the assumption is that we're going to make the assumption here that these K's are the same and these B's are the same. And actually, technically, so are the I's. So I'll even write I2. The angles are different, though. So we assume the inertias, because they have the same disk and the same number of... Technically, they're not going to be exactly the same, but for all intensive purposes, we can assume that. If you were in your company and you decided you wanted to know it exactly, you didn't want to make that assumption, cool, then don't. Okay? All right, so there it is. There's our our sixth order system. Second order, and second order. And remember, don't get bogged down. I just find the differential equations are exactly the same if it was translation versus rotation. So I'm kind of drawing them translationally, but noting their rotational constants or variables. Excuse me. So Now, the problem is, as I was getting to with the higher order system, is sixth order system, I've got a ton of parameters I need to find. And what am I going to do? Do some kind of experiment and then record all three thetas and then try to figure it out. It's doable, but again, it's pretty messy. So I got a trick. All right. Now remember, this, yes, if it was a satellite, this would be a difficult trick. But then again, technically, I've got the satellite in on Earth initially, so I can do any experiment I want. So I want you to remember that before you send this, whatever this thing is you're trying to identify the parameters of, if you're in a lab or in the in the work setting, and you can maybe take off a component to do an experiment on just a piece of it, then you should, okay, to simplify your experiment. So that's exactly what we're going to do. What we're going to do is we're going to lock down the middle disk. All right. So what happens is that makes the middle disk ground. Okay. Because it won't move. So it's 0. So it's ground. So I'm going to, if I lock the middle disk, so lock the middle disk, watch what happens. I'm going to redraw them as such. Well, basically, I could draw the spring and the damper on the same side, but it makes no difference for the differential equation. You could move that to this side. Theta 1. So there's one system, and here's my second system. I2, theta 3. And B2. So look at this. This is awesome. What did we just do? We just took three coupled second order systems, which makes a sixth order system. We decoupled the system into two second order systems, totally decoupled. So I can do an experiment on this, which is a classic second order system, which we know a lot about. And this is a classic second order system. So we just do two experiments independent of each other and figure out, and then of course the whole goal is to use that experiment to figure out, what are these values. Now notice their B's are going to be quite different and their I's are going to be quite different, but their K's should be, very similar. Okay. Awesome. What's next? All right, so now comes the challenge of finding the coefficients. All right. Now, there's two ways to find the coefficients. There's an experimental way. If you have the physical device, there's that you're trying to estimate the parameters of, then you can do it via an experiment. Okay. Excited, get it, do a step response, look for overshoot, those kind of stuff is possibility. Settling time, rise time, we saw that in the homework kind of stuff. And this is kind of what this lab is about. I'm doing it slightly different experimentally, but very similar. The other way is theoretically. You can measure, if you physically have this, you can measure, or from SolidWorks get all the dimensions and the material properties, etc. And use your knowledge from, mechanics of materials, solids. How do you calculate the torsional stiffness of a rod? How do you calculate the moment of inertia? If you have all these, if you can measure everything and you know the dimensions and the material properties. So this is where it's your turn to start Googling, those kind of equations. But before we get to the theoretical way of doing it, I want to first talk about the experimental way. So you're going to do it both ways in this class. And let's talk about the experiment. Let me think. I'm going to stop here and then start a new short video with the experiment. All right, so we're going to talk about the experimental way to find these parameters. Okay, now remember, we're going to do a single experiment, but we're going to do that experiment twice. So we're going to do one for this system, one for this system. So the bottom disk and then the top disk, but they're independent of each other. Okay, so I'm just going to talk about the single experiment, and you'll just do it twice. Okay, so what we're going to do today in this lab is we're going to take this torsional system, we're going to pull it back, and we're going to do an initial value problem. So we're going to pull back, and we're just going to let go. And it's a second order system, and it can be easily shown that, well, let me show you what it looks like. You can imagine if it's an underdamped system, here's your initial condition, it's going to look something like this, you know, ... Okay, that was pretty bad, but the end. So, and you're going to see that this is going to have some decay rate, right? And it's going to have some frequency of oscillation, all right? And it turns out that given your second order, so here's your transfer function of your second order system, classic spring mass damper slash inertia mass damper, spring inertia damper. Okay, we derived that too in one of the homeworks. And remember that I can make that equal to k hat omega n squared over s squared plus 2 zeta omega n s plus omega n squared. So we can relate those. We did that before with the spring mass damper. And we showed that the pole locations, which tells you a lot about you know, the response, also the initial value problem. The poles are at S12 equal to minus zeta omega n plus minus j omega n squared over 1 minus zeta squared. Or equivalently 1 minus sigma plus or minus j omega d. Okay, so that's omega d, that's sigma. So obviously this is going to give you your decay rate, and omega d is going to give you frequency. So what we're going to do is you're going to figure out, you're going to use MATLAB, you're going to record this data. Well, technically I recorded the data, but I'm going to give it to you, but pretend that you recorded it. You're going to record it, and you're going to fit a complex exponential. So you're going to fit y of t is equal to some c e to the minus sigma t cosine omega dt. That's what we're going to do. So you're going to fit the best of the of that function on this signal. Now, be careful at the end. I would cut off at some point, X out some of this. The end stuff gets nonlinear because of stiction, because of Coulomb friction. So that Coulomb friction is nonlinear. So be careful. The velocity starts to get small here, and it starts to become garbage from a linear system perspective. So you want to get a good, good number of periods, but not at the end. And you're going to fit this. Now, how do you fit it? Well, there's a few different ways. I'm going to let you figure it out, okay? But you could use, one example is use nlinfit. That's a function in MATLAB. You don't necessarily need to do it that way. But if you were taught that, for example, in data analysis, then you can use that function in MATLAB, okay? So once you fit this function, that means via the experiment. So first you do an experiment, then you fit, and you get sigma omega d. Now from sigma and omega d, you can relate that to omega n and zeta, right? That shouldn't be a problem, okay? Via this equation. And then from omega and zeta, you can then relate that back to, technically, to b over I and k over I. Okay, if I was to relate these, I need to divide by I. So here's where you have a little problem. Here's two equations, but I have three unknowns. So in this specific experiment, you actually need to assume, you need to use one of your theoretical values for either, one of your theoretical values to get the other two values. Okay. Now, just as a little foreshadowing, there are, mechanics of materials, solids, tools that you can approximate I theoretically and K theoretically. But B, the damping, the energy loss in that system, that's so hard to find. It's a function of the pulley tension and the age of the bearing and the bearing itself. Forget it. It's not something that's even worth trying. This is why, if I was doing this system, analyzing the system, one of the biggest reasons to do this experiment is to find B, because I don't have a theoretical value for that one. All right, so that's it. That's the experimental, and you're going to do that for both the top and the bottom disk. And you're going to get, if you assume the K that you find theoretically, then you'll get an I, you'll get an I and a B from this experiment, or I1 and B1. And then the other experiment will give you I3 or I2 and B2. And remember that we assume that the middle disk, even though it's locked down, we assume the middle disk is the same as the top disk. So whatever you find for the top, that's the parameters I would use for the middle as its parameters. All right, sweet. So that's the experiment. And now actually, let me just say a few things. I have a couple videos of me doing the experiment so you can see it. And then we're going to move to the theoretical option of how do you find K and I theoretically. And we'll talk a little bit about that in a second. All right. Now here I'm going to lock the middle disk. Can you see that? I think so. Okay. And why am I locking it? Well, hopefully we talked about it. We're locking it so that I can create a ground and separate the bottom disk from the top disk, and therefore creating a two second order systems instead of a total of a sixth order system. I just want to show you what the initial value problem experiment would look like. Okay, so I would pull it and give it an initial value, and then let go, and then record the data and watch it decay and oscillate at what frequency. So this is the data I would have I did collect that data, not this one specifically, but one similar to it, and have posted it onto Canvas with the lab write-up. Now this is again the initial value problem experiment, but for the top disk instead of the bottom disk. A couple things you'll notice when comparing the boundary value problem experiment for the bottom disk is that the top disk is faster, has a faster frequency of oscillation, and also the oscillation lasts a lot longer, doesn't decay as fast to zero. All right, so in this lab, I also expect you to do the find the parameters, except for the damping. I said that that's not one you're going to find theoretically. Find the parameters theoretically. So, and that would be the mass moment of inertia and the of the top disk and the bottom disk, and that they're going to be different, obviously, because they have different amount of brass masses. Hint: you probably remember this word, this concept, the parallel axis theorem? You remember that? That's probably like, oh yeah, I remember that. So you might have to do some Googling, but figure out how to find the mass moment of inertia. Of course, the only thing is you need to know the dimensions and the material properties and stuff like that. So in normal semesters, I actually leave out scales and calipers and tape measures so that the group, and I bring these physical things out, and I let the groups go and do these, dimension and material calculations. But in this, virtual way of doing it, I go through the process of measuring it, and I recorded it. So I'm gonna, those are gonna be coming up in this video, is all those dimensions that you're gonna need. Okay. And then you'll have to Google some material properties. For example, the rod is made out of steel. I don't even know what steel. So you just have to choose one and go with it for this lab. But hopefully in the real world, you would know which steel, in the working world, you would know which steel it is. So now in terms of the stiffness, so that's mass moment of inertia. You'll just have to refresh your memory. And I'm okay that you don't necessarily remember it, but you know where to look. Google or your solids book. The other thing is the stiffness, the spring constant of the rod. So I don't know if you all remember, but you can measure you can calculate stiffness of, for example, beam, which is something like, do you remember EI over L? Do you remember, I think that's actually axial stiffness rather than bending stiffness of a rod. But, and so you need to know E, you need to know I. That I is the area moment of inertia and the length of it. Okay. But in this case, this is not those situations. This is a torsional. We're looking for the torsional stiffness of a rod. So you'll just have to go digging and find that equation. And once you find that equation, you need to know material properties. You need to know very similar to EI over L, but it's not EI over L. Let's see. And yeah, so that's the gist. All right. So you'll by the end of this theoretical way, you'll have a value for K and for the two I's. All right. And yeah, so the next thing is doing all the dimensional measurement on this system, and that's coming up right now. All right. Awesome. Now, if we were in person, you would be doing these measurements yourself. But since we're not, I'm going to do them for you. And we're talking about a foot. So that torsional shaft or rod is 1 foot between the discs. Both the middle to top and middle to bottom, we can assume a foot. Now let's measure the shaft diameter. Again, you would normally be doing this yourself. So I'm getting, it just depends, 3. Up there it's 3 exactly. It's around, hard to say how I'm holding it with the camera, holding the camera too, but I would say, I'd say 3.1 millimeters diameter. So the disc, each one of these rings is 1 centimeter apart if you look at the manual, except for the first one. I think it starts at 2 centimeters. Then it goes 3, 4, 5, 6, 7, 9, 10 centimeter radius disc. All right, let's go ahead and measure the thickness just to have, and I'm getting I'm getting 4.7, 4.7-ish thickness. Let's measure the brass mass. I did forget to say that the disc is aluminum. The brass is 500 millimeters diameter and about 30 millimeters in thickness.